Welcome to Playing with Junk again. You have probably seen this clock here in one of my previous videos. And well, in fact, it's not really a clock because something very important is missing. It has no crystal inside, it has no clockwork inside. It's only a motor that moves the minutes, and this motor needs an impulse every minute, a positive impulse for 1 minute and the next minute a negative impulse to switch the minutes. So it's basically only a time display, not a clock. And I had this connected to my main clock, but that turned out it has a bit an issue. Sometimes it works perfectly for weeks and sometimes it misses 10 minutes the next day, so it's not really reliable. Well, so I thought I can solve that problem, and I did, and this is my solution. I will show you the schematic diagram a little bit later and explain how it actually works, but at the moment I want to assemble the PCBs. And in fact I got another package from my favorite PCB maker, PCBJ. Well, it's my favorite PCB maker because they made my first PCBs and I like how they are working, and they are quite fast. They are shipping with DHL, and it takes about 1 week from sending them my designs to actually getting back finished PCBs. I just ordered 5 pieces because, well, you never know, maybe you need more master clocks for more slave clocks. I like the service of that company. You send them your files. I use KiCad for designing my schematics and PCBs, and it takes normally, well, less than an hour until they reviewed the files and told you that everything is okay, or maybe there is a problem and should they fix it and how should they fix it. So very nice. And it takes about 2-3 days to actually manufacture the PCBs, and then they send it with DHL, which is a little bit more expensive. In fact, the shipping was almost the same cost as the PCB, so I don't have the numbers right now, but I think it was $25 for the 5 PCB, so it's about $5 per board, and about $20 shipping, so $45 5 PCBs. I mean, in 1 week, that's way better than making them myself and less messy, and they're really professionally made, and it's exactly how I ordered them, including my Play with Junk logo. Okay, let's assemble that. And hopefully I did not make an error on the PCB. We will see. Okay then, that's it. You see the LED is blinking in a 1 second speed. Probably the relays are clicking in 20 seconds. That's the push button to reset the seconds to 0. So every time my atomic clock here, my receiver, jumps to 0, I push the button, resets the seconds and starts counting 3, 2, 1. That's it. And it seems the slave clock is also counting the minute. Okay, 5, 4, 3, 2, 1. And it's 20:38. Yes, okay, let's have a look at the schematic diagram and I will explain how this thing actually works. Okay, that's the schematic diagram of my main clock, 1 minute bipolar driver for slave clocks that need a bipolar signal. Okay, we start at the crystal here. It's 32,768 Hertz. That's a standard clock crystal. And it has this frequency because that's 2 to the power of 15. Yeah, I think. So if you divide this 15 times by 2, you get 1 Hertz. And that's exactly what we do with this chip here. It's a CMOS 4060 chip. They come from different manufacturers. And it has an integrated oscillator here. And then all the Q4 to Q12 are dividers. I'm using Q14, that's 2 to the power of 14 dividers. This one has now an output of 2 Hertz, because that's 2 to the power of 15. We have to divide it 1 time more by 2. And that's happening here in this counter here. So here we go in with 2 Hertz. And we count binary 4 bits. And we have cascaded here the second part of the same chip with another 4 bits. So that's an 8-bit counter in total. And you see on output 0 we have the 1 second blinking LED. This is directly driven by this LS74LS chip here via a 1K resistor with a voltage of about 5 volts. That's probably we are dropping here 2 volts, so we are talking about 3 milliamps here, and we are going to ground here every time when Q0 is low. The LED lights up, and tying to ground the input, the maximum current for this chip is about 10 or 15 milliamps, so we are on the safe side with 3 milliamps here. We can drive that LED without problems. And it's a high efficiency LED, so even with 3 or even with 1 milliamp, it's bright enough to see, and that's all we need. Then we have that chip here. It's an AND gate with 4 inputs, 74LS21. And we are taking the output of bit number 3, 0, 1, 2, 3, which goes to the next counter, and then we take bit 4, 5, and 6. That would be bit 7, we don't need that. And if all the bits are high, that means we have a number 60. We counted to 60, and that resets. Here are the master reset pins for the two 4-bit counters, which are together an 8-bit counter. So we counting to 59, and at 60 we reset the whole thing to 0, and we start counting again. That's our minute. So every minute there is a reset here. This reset goes through this OR gate here, and that has a reason, because we have the switch, the reset switch, the manual reset here, which also goes to that OR gate. So either the switch does reset my counter, or the number 60 sensor here resets the counter. So this, or both, of course. But you don't need to push the switch when it's already resetting. Okay, then we have this 1 minute pulse here going to this chip. It's a 74 LS76, and that's a JK flip-flop. Well, what we need is this. We have to energize one relay or the other to give the slave clock 24 volts on that pin and ground on the other, or 24 volts on the other pin and ground on that pin. So every minute we have to change which relay will provide power. And that's what the JK flip-flop does. We have pin 1, it's the input. J and K are tied to 5 volt. And that means every time we have a high pulse on the input, that changes, and Q gets high, Q not gets low, or the other way around. Now the next problem is, I don't want that my clock gets 24 volts for a whole minute long, and then 24 volts in the other direction for the other minute, so that will probably overheat the coil inside this slave clock. So what I need is a short impulse of maybe 2 seconds. So that relay should be on 2 seconds. Then wait a minute, and then the other relay should be on for 2 seconds, and wait a minute. So that's what I do here. Let's say Q is going high, like that, high. This transition from low to high will pass that capacitor. It's a 100 microfarad, it's a relatively big capacitor. And then after the capacitor, the voltage will decay, because there is a resistor here which will discharge the capacitor. But that takes a while. So, and with this combination, 100 microfarad and 47K here, we get a high impulse for about 2 seconds. And then we have another important chip, 74LS14. That's a so-called Schmidt trigger. And I see that's not the right symbol. Normally there is a hysteresis sign looking like a S here inside. A Schmidt trigger, well, in this case it's a Schmidt trigger and inverter. A Schmidt trigger on the input has a defined on voltage and a defined off voltage, and there is a difference between the on and the off voltage. So a normal TTL chip has a value of about 3 to 5 volts where it decides to be, this is a high signal, on, and it has a voltage from 0 to maybe 1 or 2 volts. No, that's too high. So 0 to 1 volt maybe, where it recognizes the signal as a 0. And everything between is not allowed, because you cannot say what the chip is actually doing. So if you put in 2.5 volt on the input, it is possible that the output will oscillate on off, because the chip cannot decide what to do. And that's something we can avoid with this Schmitt trigger. So the Schmitt trigger turns on at, let's say, 3 volt. Depends on which type we take. There are 7414, 74S14, LS14, all kinds. They have different voltages. You can see that in the data sheets. Let's say at 3 volts it turns on. So this impulse here goes up to maybe 4 volts. Takes a while until it drops to 3 volt. It's still on. And then it drops further, and at the level of, let's say, 2 volts, this Schmitt trigger decides it's now time to switch off. And it switches off and stays off. And when the voltage rises again, it stays off until the input here reaches 3 volts. And that means if we put 2.5 volts, it depends on which state we had before. So we cannot, the Schmitt trigger does not oscillate between two values, because it needs at least 1 volt difference to switch on or off, and that's what we do here. So we have an impulse going high, going slowly down, and after 2 seconds this turns off that transistor, or for 2 seconds it turns that transistor on. The relay clicks and we get 24 volts to that pin, or we get 24 volts to the other pin. And when the relay is not energized, the contact is on ground. So the most of the time both contacts here, 1 and 2, are ground. Of course nothing happens, even if we have a short circuit or a short to earth or whatever, no problem. And for 2 seconds we get 24 volts on pin 1, and a minute later we get 24 volts on pin 2 for 2 seconds. Just enough time for the clock to switch. You probably see we also have a couple of diodes. They have their own purpose. These 2 diodes here are to eliminate the return voltage from the coil from the clock. So that's back EMF. If you have a coil energized and you switch off the power, the magnetic field decays and generates a back voltage here, which can be quite high. It even zapped my finger when I touched the crocodile clips. So the 2 diodes here clip this high voltage, which is in negative polarity, clip this to the ground, and the circuit here is safe. And the same for the relay. There is also a coil inside, a much smaller coil, but also this will generate back EMF, which could destroy the transistor, but with the diode here we are on the safe side. Okay, that's that.